Question 1. Now, these questions are the first questions on your paper 2, and they always relate to things that you may not have seen, but the principles behind looking at proportionality and so forth need to be applied. So we're going to go through quite a few of these examples, and you'll see that although you may not have seen it, by using these basic principles you can follow through. So this question is about electrical resistance of the metal mercury. So it says the resistance R of a sample of mercury was measured as a function of the temperature T. Now this big T over here is your Kelvin temperature. So that's the temperature where you start at zero, at absolute temperature or absolute zero of the sample. The sample was cooled and the data points were taken at temperature intervals of 0.2 Kelvin. The uncertainties in R and T are too small to be shown on the graph. So we've got here, we have our R versus T in Kelvin. It said that it was taken in samples intervals of 0.2 K. So when you look at your temperature here, you can see that each one of these small blocks is actually 0.1 K. So a small block is 0.1 K, and you can see that there's 2 blocks apart from each of these, 2 blocks, and so forth. So we will look at that. All right. Then it says the hypothesis, the prediction, is that resistance is proportional to the absolute temperature for temperature greater than 4.5. So starting at 4.5 over here, saying that it is proportional. Now, if I was looking at that in mathematics, it would read R is equal to some constant, I'll call it K, times T. And the graph that you would expect for that is a straight line going through the origin. So you would be starting at 4.5 and you'll be getting these values over here, and they should be forming on a straight line, and it should go through the origin. It should go through the 0, 0 point. So that's prediction. So suggest whether the data supports the hypothesis. So is this a straight line? So it's no, and the reason for it, you can't just say a yes or no answer. You have to give a reason to get your 1 mark. Data is not a straight line, and also does not go through the origin, not go through the 0, 0 point. Then it says draw a line of best fit through the data. So firstly we see we've basically got 2 parts. Now when it says over here draw a line, that doesn't mean a straight line. This can be a curve, but it's just got to be a line. But you see, when you're going from along here, you can see that here you do have a straight line. It seems to go there, and then you suddenly get a change and you get a curve forming there. So that would be your line through your data. For B, state the value of R for which the rate of change of resistance of the sample with the temperature is least. So it's the least over here, and that is obviously 0 for up to here, up to this point over here. Your resistance is R, so 0 ohms. We have our unit is ohm. Looking at question C, I'll just read these through because I need to go back to the graph to actually answer them. So at a temperature Tc, the resistance suddenly becomes 0. So we have the switch over to becoming 0. Use the graph to determine the possible range of the temperature Tc. State the correct number of significant figures the value of Tc and its uncertainty, and outline how the temperature Tc could be measured more precisely. And then we've got for D, outline 2 reasons why you could not use the data to determine an accurate value for R at room temperature. So those are the questions that we'll be looking at. So you can keep your page open there, but I need to go back slightly here. There I am. So we want to use our graph to find a possible range. Now we can see that this value over here we have, and this value over here we have. So we're actually going from 4.2, the range would be from 4.2 to 4.4 Kelvin. So if you have a look here, this is 1, 2, and this is just below is 1 below. Each small block is 0.1 of a Kelvin. So that would be your range. Now, state the correct number of significant figures, the value of TC and its uncertainty. Well, it's in this range over here. It's between those two. It's between 4.2 and 4.4. So we would take halfway in between. So for C2, your value for TC would equal 4.3 K, midway between the two, plus minus 0.1 Kelvin, because that would give you from your 4.2 to your 4.4. Then it says outline how the temperature TC could be more precisely measured. Well, you would want a measuring device that is more sensitive. So you'd want a more sensitive measuring device, something that can, because this over here can only measure intervals of 0.2. So you would perhaps want something that can measure 0.05 Kelvin, and then you would be able to more accurately find that value, more precisely find that value. So if you had something with that could measure at smaller intervals, you would get a more precise value. And then finally, the last question, outline 2 reasons why you could not use the data to determine an accurate value for R at room temperature. So for this data, we are talking about extremely low temperatures. These temperatures are very low. And we don't know if this trend will continue. We already see that there was a change here. Perhaps somewhere up here, somewhere, there will be a further change, for instance. So we're not sure that there will be the change. We know that mercury, for instance, it's Hg as its symbol, is a liquid at room temperature. So perhaps that will cause a change. So there's no ways really of knowing that this data could actually predict your temperature at much higher temperatures, 273 Kelvin, which is 0 degrees centigrade.